when it restores the file will have root will be owned by the root, right? Because this file is being created by a root program, therefore the file will have root ownership. So what this program has to do is, because it's your file that it is restoring, it needs to change the user ID back to your program. So now there can be a race condition between so let's write that down a little bit more carefully. Okay. So let's think about the restore operation. So what it's going to do is create file from backup, right? And then okay. So so what can happen is, let's say the file is so if you do it this way, right? So suppose the attacker backs up a program that has a setuid permission. Okay, there is so then what can happen is that at this point, right, the setuid permission on the file is restored. Right? But this is not safe because the setuid permission should have been set with the file owned by the normal user, right? Because at this point in this window, what you have is a situation where the user is able to run this program, and now because it is still owned by root, right? So you have the setuid permission of the root, and so that creates a vulnerability. So there is also a race condition that involves things like RM. So let's look at what that is. So so it depends on how this program RM operates. Okay, so the program RM has this option -R, which is used to remove an entire directory tree. Okay, so what can happen is, let's say the attacker creates okay, so and then has a bunch of files here. Okay, so what RM may do is RM may descend into this. Maybe it'll do it. Suppose that RM goes bottom up, right? So it goes to the innermost directory and then deletes everything here and then moves up, right? And then, so this is the first, it removes these files, then it removes these files, and it removes these files. Okay? So what the attacker can do is they can rely on this, right? And when the RM program is executing, removing files inside B, the attacker can move, right? So for now, right, think of this as, so this has been moved by root. Okay, so root is trying to sort of clean up the /tmp directory. Okay, so if the root process has gone here, right, but the attacker owns these two, right? Directories A and B, they own these two. Okay, so what the attacker does is they rename B, or rather they move B so that it is here, right? So RM, after removing all the files within B, it goes to ... Okay, so it thinks that ... will get it into A, and that it should remove these files. Okay, and then after finishing A, it should do ... and remove everything in /tmp. So it's going to go 2 levels up and remove the files up to there. Except that once B has been moved over there, 2 levels up will be /, right? So RM may end up going there and removing all the files. Okay. So once again, this is a kind of a race condition because the privileged program is believing that a certain condition exists, but the condition, although it was true at the beginning, has changed while the program is running, and as a result, the attacker is able to carry out certain attacks. So the more interesting thing is the races themselves are not, what is more interesting than the races themselves is how the attacker can succeed in races. Right? So because what I'm saying is a typical case. Right, let's go back to access and open. Right? So what the attacker does is they initially create 2 to be a symbolic link. Okay? And it is a symbolic link to, let's say, okay, let's make a and so on. Okay? So now, when this access is performed, the operating system is chasing these symbolic links, right? And then remember, each of these is just a plain file. So essentially, the operating system has to go and read this plain file. So to follow many links can take a while, okay? And this can be made even harder by not creating /tmp/a2, but you could create everything, in a directory that's 1,000 levels deep, right? So each of these may not contain a name that's like 8 characters, but it may contain something that's 2,000 characters, and when you and not only 2,000 characters, it has a lot of you have to traverse a big directory tree. Therefore, this whole thing going up to all the way to A1000, right? Because when you do access, what the operating system is checking is whether the target file here, right? You have access for that, okay? So it's going to follow all of this, and because the attacker creates this structure, they can make it, as complex as they want, and it can be made, to take a very long time, okay? The catch is that the operating system has a certain limit on the number of symbolic links it's going to follow, right? Because one of the things I said about symbolic links is that it can point to directories, whereas hard links cannot point to directories. And the reason why this came about was because the operating system doesn't want to get into a situation where it's in a loop, right? So it doesn't want to go into a cycle. So one way to avoid this is to make sure that hard link can never go to a directory, which means that hard links always go to the leaf. So therefore, you cannot have a loop, right? So for symbolic links, because we want the flexibility to go to the directory, now there is a possibility of creating loops. And the way the operating system protects itself is by saying you can only follow symbolic links up to some maximum number, and it could be like 1,000. Okay, I don't remember. If you look at the man pages, it'll tell you what is the limit. So the only limit that the attacker has to respect is that this depth cannot increase beyond say 1,000. And if this is all they do, the operating system is going to be fast enough, and still it's going to be quite difficult to raise. But so what the user does is they, instead of creating /tmp/a1, they might say /tmp/b1/b2/b1000/a2. Right? So at each level, now, yes, there are only 1,000 links, but each of those links, requires you to walk down a directory tree with 1,000 levels. Okay? If this is done, now this whole thing starts taking, an appreciable amount of time, and the attacker can then succeed with like 100% probability. Okay, so that's so this was a paper. So one of the professors working here and a student came up with this attack about 10 years ago, right? So it's something that, again, attackers are always, resourceful. So we need to, whenever we make an assumption that something is hard, we need to, we need to be really skeptical, because ultimately more often than not, we are proven wrong because attackers always find a way. Okay, so there are various techniques you can use to avoid some of these bugs, but there isn't sort of a universal solution. So for instance, if you want to make sure that the setuid program does not accidentally overwrite an existing file, then you can create, you can specify flags to the open system call, okay, which will make sure that a new file is created only if it doesn't exist. Okay, so if the file already exists, so for instance, if the attacker was simply making f point to etc password, then if you open with these two flags, then that system call will fail. Okay, so what those two flags are saying is that it says that you create a file, and this exclusive flag basically says if the file already exists, then you don't create if the file already exists, just fail. Okay. So the other example that we discussed earlier is how a program creates temp files, right? And the first idea was create a file name that looks random and unpredictable. But of course, attackers always find what is this supposedly random way in which you are generating these file names, and so don't do it. Instead, use these functions that are part of the system library to create the file names. And these so these things don't create a name, but instead they just create a file. Okay, so in particular, these functions will create a name, and then they will use these flags to make sure that that the file, when it is created, is actually doesn't exist before. Okay, and then you have no problem. So the idea is that don't try to check and avoid the problem, but find a way such that the problem can never happen. Okay, because and the if you use the operating system calls in the correct way, then you can avoid having this type of permission check that's prone to this kind of race conditions. Okay. So the other thing that has been done is many of the examples I gave you involve permissions on /tmp, and the fact that everybody is able to write into /tmp. And so long ago that was how it was, right? So if you looked at a Unix box 25 years ago, then you will see that /tmp was world writable. Right? So now that's not how things are configured. They are configured with a particular option called there is so in Unix, file permissions are specified by 12 bits of information. Okay, so these 12 bits consist of, let's write this down. So there are 12 bits, okay, of which 9 are what we most often think of as permission bits, right? And these are divided into 3 groups of 3, right? So there is a set of permissions for owner, a set of permission for group, and there's a set of permissions for the world, okay, for everyone. And each of these is 3 bits: read, write, execute. So that's how the 9 bits are set up. So you can use a chmod operation to set these permissions if you are the owner of the file. Okay. So now there are 12 bits when only 9 bits we have specified what the use is. Out of the 12 bits, there is a setuid bit, and there is a sticky bit. Does anybody remember what is the other bit?
Directory, whether it's a directory or not.
That's not part of the permission, right? It's just a property of the file system node. So I'm not able to remember, but I guess that's because these two are more commonly used than the third bit. So the setuid bit we already talked about, right? It allows when normally if you start a process, then it will run with your user ID, and setuid allows a change of ownership of a process that you start. Now the sticky bit is used, it had a legacy use which is no longer applicable, so they found that it can be repurposed, and now what it means is that the sticky bit is used on shared directories like /tmp, and their meaning is that if the sticky bit is set, only although, okay, so normally when you want to remove a file, you need write permission on the directory. So this is how it works on Unix. So in a shared directory, this is a problem because you want to give everybody permission to write, because that's how they can create files in the directory. But you don't want everyone to be able to remove arbitrary files, right? So you want to say that a user should be able to remove only their own files. Okay, so one way to do that is to set the sticky bit, which says that in this shared directory, file removes will be permitted only if the file itself is writable, right? So again, see the distinction between being able to write in this directory, which everybody is able to do, versus being able to write on that particular file, right? So if you want to remove a file in a directory with the sticky bit set, you have to have permission to write the file itself. So that's exception from the typical way the bits are interpreted, and once that is in place, then the /tmp, many of the /tmp attacks become difficult. Okay. In addition, what you will notice if you look at the structure of oh, by the way, these /tmp problems, right? So one of the common ways the /tmp problems were exploited was, when you compile something, the compiler creates a lot of temporary files. Okay, and again, long ago, 25 years ago, these files would be created in the /tmp directory, and then one could use all kinds, So and you can also imagine that 25 years ago, people were